Today, we're going to learn how to implement a binary search tree from scratch using nodes. Our BST node is the same thing as a linked list node, but instead of having one next pointer, it has a left and a right pointer, which will each point to its left and right child. So the BST node will look like this. Let's also write a structure for the binary search tree. We just need a pointer to the root, which is a BST node, meaning that it has pointers to its left and right children. The children will also have pointers pointing to their children, which will also have pointers pointing to their children. And you could see where this is going. This is why we just need a pointer to the root to represent a BST. Let's think about how we can create a binary search tree. We first need to initialize a BST and then add nodes to it. Let's see how we can write these operations in pseudocode. The function BST_create will return a BST with an empty root, and we don't need to put any input parameters. We first create a new BST, and then we just set the root of the new BST to null and return that new tree. Now, to insert a new node into the binary search tree, we need to make sure the tree maintains its ordering properties. That means you'll have to place the node at the right place, where everything to its left subtree is smaller and everything to its right is greater. Let's see how we can do that. For example, in this tree, suppose we need to add the value 25. If the root is 51, which side do you think it should belong to? The left side, because everything on the left should be smaller than 51, and everything on the right should be greater. So we narrowed it down to the left subtree. Again, the root of the left subtree would be 34, so 25 should be on the left subtree, and it's larger than 2, so it should be on the right subtree, and it's smaller than 30, so it should go to the left subtree of 30. That spot is empty, so we insert it there. So to sum it up, we start at the root, compare the values, which will decide whether we'll go left or right until we find an empty spot, and then we add the new node to that spot as a leaf. To do that, we'll write a recursive function that will be called at each node down the branch. That function will take in an integer, which is the value for the new node, and it should also take in a BST node, which is the current node we're at. If I is smaller than the current node's value, we call this function again on the left child, and if it's greater, we will call this again on the right child. So we are calling this function down the tree going left or right, and let's say we met an empty spot. We can say if node is null, create a new node and assign I as the value. Then we will set the new node as node and return it by doing this. We can assign the new node to the left or right of its parent. For example, this is the state of values when we are about to call the function on node 30. We call insert BST node, and the input parameter should be 25 and null because we are calling it on node.left, which is empty. The function is going to return a new node with the value 25, which is assigned as node.left of node 30. If node is not null, this function will be returning node without any changes. But if we call this function on an empty spot, it will return the new node and assign it to the left or right of the parent. Insert BST node will be used in another function called BST insert. The input parameters are the value I and the binary search tree. And then we start the recursion by calling the insert BST node function at the root. To challenge yourself, you can try implementing insert without using recursion. The iterative version will require you to use a stack to emulate the function call stack. Now that you implemented insert for a binary search tree, what do you think is the time complexity for it? So the worst case scenario is O of n. When the tree is perfectly unbalanced, for a tree to be unbalanced means that one side of the tree has a height that is way greater than the other side. Remember from our last lecture, I showed you a tree that looks more like a twig. It's essentially a tree that only has the right children. The reason why it's the worst case is that if we want to insert 7 in this tree, we would have to traverse the whole tree from the root to the last leaf. And there are n nodes in this tree, then our insert will take O of n time. The formal definition of a balanced tree is that a tree is only balanced if 1, the left and right subtree's height differ by at most 1, 2, the left subtree is balanced, and 3, the right subtree is balanced. In other words, for every subtree in your original tree, their left and right subtree cannot have a height difference greater than 1. In our example, as you can see, the left subtree is taller than the right subtree, but only by 1. And then, if we look at our subtrees individually, we can see that their respective subtrees are equal in height. And then again, all the way to the end. Hence, we can conclude that the original tree, the left subtree is balanced and the right subtree is balanced, hence the whole subtree is balanced. Here are a few examples of trees, and let me know if you think they're balanced or not. Do you think this subtree is balanced? Nope. As you can see, the height of the left subtree is 3, but the right is 1. What about this one? This tree is also not balanced. Even though the height difference is only 1 between the left and the right subtree, if you look at the right subtree, it's not balanced because its left subtree height is 2, while the right one is 0. Okay, now that you know what a balanced tree looks like, let's think about why it's important for a tree to be balanced. The running time of insert node for a binary tree is not actually based on the size of the tree, which is n for the number of nodes. It's actually based on the height of the tree, which we denote with h. We had a worst case of O of n because the height happened to be also n, since it wasn't a balanced tree. If it were a balanced tree, then the height would be log of n. Most operations done on a tree will take log of n if the tree is balanced, like removing a node and searching a node. As you can see, if the tree is balanced, look at the relationship between the number of nodes and the height. As we said before, if your tree is balanced, we can search the values in log n time. That is a very good time complexity. Imagine you had an array that is not sorted of size 100 and you want to ask yourself, is the value 42 in it? You would have to traverse the whole array and see if 42 is in the element. However, if you had a binary search tree with 100 elements, searching to see if 42 is in your tree will only take 7 steps at most. For each node you will encounter in your tree, if the value you're looking for is bigger or smaller, you can disregard half the elements in your tree because you know the value you're searching for is not there. Every time you do that, you cut down the search space by half. How many times can you have 100? As you can see, you could half it 7 times because log of 100 base 2 is 6.6. This is actually what we call a binary search. You can perform a binary search on a sorted array too, which is what we're going to talk about in the next lesson. I think it will actually be our first algorithm lesson in our data structure and algorithms course. So I'll see you then.